Okay, we start in 1 minute. Okay, so good morning, everyone. Hope you enjoyed yesterday night dinner and the dancing. So I think we will skip the dancing morning session as we did yesterday. So this morning we are going to start with the plenary session. This is organized by the interTwin project. It's a project that is coordinated by EGI, which is ending at the end of August. So we would like to present, first of all, the context of the project is about digital twins and the digital twin engine that we are developing. So we would like to start, first of all, introducing the digital twins concept, and then in science with the short introduction. And then we have like a presentation from external projects. We have Anabela Oliveira, the head of Information Technology Division at LNIC, and we'll talk about the coastal digital twins, the projects CONNECT and WOLF. And then we will have a remote presentation from Thomas Hennen from DestinE Earth, technology partnership lead for DestinE Earth, and we'll talk about the ecosystem and interoperability of DestinE Earth. We'll then introduce the project interTwin and the main achievement, and then we will have a deep detailed presentation on the technical outcomes of the project and the scientific outcomes, so the thematic modules that we have developed and the use cases. And we will finish the session with a presentation from the Xavier Salazar on the interTwin legacy, so the impact and the collaboration opportunities. So I would like to start with introducing with a bit of history of the digital twins, starting from the first one that has been developed, let's say, considered like the first digital twin in history. So this was related to the NASA Apollo 13 mission that was launched in the 70s to reach the moon. During the mission, there was a problem in one of the oxygen tanks that exploded. But thanks to the engineer at NASA that employed simulator to evaluate the failure and extending this physical model that they have of the NASA Apollo 13 together with the continuum ingestion of data, they could run simulation, understanding the issue and the possible ways of fixing the problem, and they managed successfully to return to Earth. And this is what has been considered the first example of digital twin. Starting from there, of course, the main, there are different types of digital twins which I would like to introduce. In particular, it started from the history, the industry and manufacturing. And what we consider a digital twin and what we have been using in the interTwin project as definition is that a virtual representation of the physical object, process, or system, which is created and sustained with information that are coming from many sources of data, models, and considering also real-time and historical observations. As I said before, there are different types. So the industry has been leading this digital twin revolution in manufacturing, in particular with the goal of product lifecycle management, and with the possibility to reduce cost in the R&D, the construction, and the maintenance of their products. There are, of course, examples of digital twins also in the context of cities and airports, so smart cities, smart airports or ports. Basically, this is digital twins that they lead to design, cost reduction in design, construction, and maintenance. And then, of course, we have also the category of digital twins on the environment, which basically we will treat mostly today, which are helping with the goal of helping decision support and risk management. So with the goal of reducing cost in the preventing disaster, so risk reduction, climate adaptation, and biodiversity protection. So these are some of the examples. Of course, the time span of digital twin and what they're predicting can be different, of course, at different types, from seconds to decades. also link the white paper from Deltares, who is one of the partners of the project, which started this and classified different type of digital twins. In Europe, we have different projects or initiatives that are dealing with scientific digital twins. Of course, I think you may know one of the most important is the Destination Earth Initiative, which is the flagship initiative from the European Commission in order to create a digital replica of the Earth. But of course, we have other examples like the digital twin of the ocean, many projects which are like contributing to this endeavor. And then we have projects funded in the context of the Horizon Europe, like interTwin, which is, so they will be presented today in more details. But we have also other examples like DTG or BioDT, the e-brain health project, and also which more or less they're finishing at the end of this year or before. And then new project that we start or are starting in 2025, mostly related to weather and urban air and interactivity, which has the link to also to Destination Earth. I would like then to, given this introduction, to leave the floor then to Anabela, which will start and present the project CONNECT and WOLLF. Thanks.
Okay, good morning, everyone. My name, I'll introduce myself while they switch the slides. I'm Anabela Oliveira. I'm a researcher at the National Laboratory for Civil Engineering. I was a coastal engineer for 20 years. I've been in charge of the information technology division at LNIC. So I represent here both the IT vision and the end user's vision. And I would like to present to you what we have been doing to build coastal digital twins with the needs of the institutions that manage the coast require. And this is being done in the scope of two projects of very different complexity. The CONNECT project, a very complex with many requirements project, and the WOLLF, an application of digital twins to Africa, with all the requirements that we need there, in particular in terms of context, the internet access, and etc. Okay, this is not just my work. I have here a long list of authors, people from my division, IT people, and also people from the Coastal Zones division. Okay, so just some context here. Why do we need these? Typically, people think about digital twins as good ways to anticipate emergency actions and also to look at climate change. We need something in the middle. We need the digital twins to be the tools that our end users use every day. In the same, thank you. In the same way they read tide tables and look at weather forecast, we want them to use coastal digital twins as their everyday tool. So what is the vision here? And I'm going to ask for your attention for that red arrow there, okay? That is the key here. That is what is different in digital twins. So we start talking with the end users and look what they really want. Not our vision of digital twins, it's what they really want, so we can address societal needs in a very meaningful way. So we start there through a number of social science tools to bring in their requirements into computational issues. Then we have the big orange box, and there we have a lot of things that interact with each other. Starting at the right, we need to bring in all monitoring devices that we can get, okay? Our digital replica, like Andrea said, needs to be precise and accurate. Then we need to interact those with the models. We need models to represent what is going to happen in the future and also to replicate the past, to give confidence on what we are doing. Then, in order for these things to be available to the end users, we need services. We need computational services, and most of the work of my team is not on that middle block that starts with OpenCoast. That's where we mingle data and models to provide services. And all of these, of course, reflects to the needs of the end users. I'm going to spend 1 or 2 minutes just talking about what these computational services are, because they are at the heart of digital twins. So what we need them to be? We need them to be generic and applicable everywhere. So we are not going to replicate for every system. We are going to have tools that do that for us. We need them to be flexible because today we are using model schism, but tomorrow we can be using another model. They need to be robust enough to operate in automatic ways. We don't have enough people to implement digital twins all over the world without technology. And we need them to have user-friendly interfaces because we want end users to be able to build digital twins. Okay, we have here two examples of two of our services that probably you don't know that well. Warsica, developed in the EOS Synergy project, that allows people to interact with Sentinel-2 images in an automatic way and get water indexes and build, for instance, delimitation of the coast to build new models. Then we have artificial intelligence, because we need inputs from rivers, but rivers have lots of dams and hydraulic structures, so just using hydrologic models is not enough. So we have been building a service that allows people to select the monitoring network, the stations they want to use, and produce river flow predictions in an automatic way. Okay. Probably the best well-known service that we have developed, OpenCoast, it handles the whole forecast system cycle. And to do that, we link work that has been done outside our group, done at NOAA with Jigsaw and OCS Mesh, and we now have the ability to go through a simple interface the whole forecast system. And why is it important? Because through the service and through this user-friendly interface, the users can build their own tools independently without having to ask us for anything. And all of this, of course, is supported by federated computational infrastructures. Okay, now I'm going to show a little bit how we have been applying this to two projects of different dimensions, different requirements. And the way we make this happen is through coastal observatories. Coastal observatories are our powerful interfaces that are very easy to use, but they encapsulate all the results that are needed to address the end user requirements. And this is built and tailored for each end user, okay? Doing a compilation of services behind the scene. Okay, let's start with the CONNECT project. CONNECT project and the CONNECT Plus project, and it's two sequence of two projects funded by the CMEMS downscaling program, where we link our products to the CMEMS products in a seamless way, and we produce digital twins that address the local users. And we have been applying this to the Portuguese coast, very different type of systems from the Tagus estuary to the Formosa lagoon in the south. And in each of these digital twins, we build the twin according to the end user needs. So they are different. Each of the application is different because it's tailored to the local end user needs. Let's look at the architecture behind all of this. So we have in the center what is the main core of our coastal observatory, the twin. And then we have the linkage with the end users to the web GIS portal. Notice that we have a lot of connections with the outside providers for atmospheric predictions, for ocean predictions, for river flow data, and all of this is combined in an automatic way that produces relevant information for the end users every day. So just a little bit of detail on the building blocks of CONNECT. For instance, for the Tagus estuary, we had a very specific requirement, which was to address water quality and inundation. But in order to be efficient and to use computational resources efficiently, instead of having a very large model with 3D properties across the whole of the domain for the inundation area that you can see on the left, we decided to have two faster and more agile implementations of OpenCoast. And you can see on the boxes the service that we are using for each of these products. Then we also use outside services. CoastNet is a service, a computational service, that provides information for remote sensing and in situ data sets in Portugal. So our system is open to incorporate inputs from other people. This is just a view what the end user sees when he enters the CONNECT digital twin for the Tagus estuary. On the left, we have model products, the ability to move around in space and in the vertical in time for the specific variables. And then a tailored dashboard on the right, where the end user puts the graphics that he wants. If he wants to look at salinity but not temperature, he can eliminate one and put in the other. CONNECT is very detailed digital twin, so we had a lot of dashboards for a number of services that you can see there. So each of these is provided automatically every day and configurable by the user. From the reality in Europe to the reality in Africa, we have the WOLF project framed in the UN Decade Initiative under the D2 program. And there we wanted to build digital twins to support water quality issues and fisheries. And there the concern was to be able to address the local community's uses. So we wanted something to be very simple, so the fishermen could go to the interface and look at it. The interface needed to be simple enough to work in a mobile phone with low quality internet. So it was a completely different type of requirements from the ones we had in CONNECT. So this, oh, by the way, and this is a work done with the people, the universities in Cape Verde and Nigeria, and also with several NGOs. So this is an example of our interface for WOLF. So it's very simple, very easy to use. People select the site, and then people look at very simple products, but tailored to their needs. And we address one issue that sometimes people forget, which is translation to local languages. For instance, OpenCoast is going to be translated to 13 Nigerian dialects. And that is the key to have the local people use it. Most of them don't speak English, so they won't be able to use it. So I know I've been talking a lot, so I'm going to wrap up. So what is the way ahead? Most of this is related to forecasting and short-term concerns. We are moving OpenCoast and CONNECT to hintcast and climate change and engineering intervention scenarios. At the same time, we are going to strengthen our connection with social sciences. So we want to build on top of this a consensus tool that helps end users with conflicting uses to use the coastal observatories, the coastal digital twins as a normalization tool. Finally, this is very nice, but building the observatories is not a relocatable issue yet. So we are looking at the work that interTwin and other providers are doing in terms of infrastructure for digital twins, so we can build a builder of digital twins, something that automatically builds the whole value chain through a simple interface. And I wrap up with my funding providers, and thank you all for your attention.
Thanks a lot, Anabela. So if there are questions from the audience, you can also use the app, and then we can reply also later if you want. But any question now? Okay, Paul?
Now?
Yeah. Magic button. So thanks for a very interesting talk there. I'd maybe ask a very awkward question, but it's one that I care about in other contexts. Do you have a plan for sustainability on because you mentioned various computing resources, so and providing a service. Do you have a way of funding those services and achieving sustainability?
Well, the way we work for this type of work and others that we do at LNIC is that we have a development chain. We start with research projects that develop the tools, that demonstrate the tools, and then we integrate this type of work in broader projects that we do for the end user, the port authorities, the water institute. For instance, CONNECT is being used right now to address one specific issue at the coastal site funded by a port authority. And of course, we continue funding the development through research and innovation projects.
Okay, so the port authority would then pay for access to that service?
Yeah. They will get the use of the service tailored to their needs. Yeah. So this is all open source. You can, if you browse for WOLF in the net or CONNECT, all of the products for the implementation sites are open to everyone. Actually, that is part of the requirements of the projects. And for new implementations, yes, the authorities pay for us to implement, to tailor the products to their needs, okay? Usually in the scope of broader engineering projects, okay? Not led by my division, led by colleagues from the Coastal Zones division. So that's the two-way we continue to develop and to interact with society. That is very important for us because we researchers tend to think that we know what they need. We are completely wrong, okay? And they have very good ideas of what they really need from us.
Good, thanks.
Thanks a lot. Tiziana?
I have a related question. I was wondering how your laboratory, your engineers support these tools which have so broad adoption and broad applicability worldwide with South Africa and other regions. So is your team also engaged in technical support? How do you do it?
Well, when there are issues, for instance, someone has troubles setting up a grid or something like that, they reach out for us and we typically help them to overcome the problem. So it is important for us that people are able to use the products without problems. And that is something that we invest some time doing that because I think it's part of the process. If we want to keep something alive, we need to help the users to overcome problems. At the same time, we take advantage of those interactions to see what is missing in our value chain. So we will see what are the IT tools that we need to put up in place so in the future other users won't bump into that problem. Okay.
And I assume the model, the tool is deployed by them in their own laboratories with their
intermediate steps, sort of. So this is also exemplified here in this slide where we present and want to explain that it also means that for Destination Earth and for the project that we are working with, interoperability is not like a single thing or single concept. It's very much very different for a different type of application depending on how they want to be linked or how they want to use Destination Earth or how they want to contribute to Destination Earth, either fully integrated, so we can foresee that certain models will be fully coupled with Destination Earth on a model level, where certain processes will feed into Earth system models and vice versa. We can also see that, similar to interTwin, we couple on the component level, so on the, for instance, the workflow manager or the data handling components and so on. But we can also see that there can be integration on really like on a consumption level, where applications or users will just use data or information that's being produced by Destination Earth, but not necessarily have a tight integration with the Destination Earth. And all of these are perfectly fine, and we're working on solutions for all these different scenarios. So for interTwin, on the left-hand side, you see a very high-level abstract representation of the Destination Earth architecture. On the right-hand side, how we map the similar components into interTwin, and where we see opportunity to link them depending on the use case that we want to integrate. So at the moment, most of these use cases are very much on the data axis, also in the collaboration with interTwin, where we just try to understand how we can move data between Destination Earth and interTwin. That means that from the quite rich landscape of Destination Earth, most of the initiatives with interTwin are really on the right-hand side, on the consumption side of the spectrum, using, for instance, data handling components in Destination Earth like Polytope, using maybe components like EarthKit and so on, but not necessarily interfacing with the components on the left-hand side directly on the model level. For other cases, we actually do that. So if you look at the climate digital twin, the examples that we have here, so we have on the left-hand side the different models that we're using to generate climate scenarios. And then on the right-hand side, you see the different impact sector models, but also monitoring evaluation framework, applications that will generate statistics about these climate scenarios, and that tap directly into the data stream while the model is running while the data is being produced. And that is a concept that we also would like to explore with more use case, because I think it's a very powerful way of integrating with Destination Earth. Of course, for us, artificial intelligence, machine learning, AI machine learning is becoming more and more important for two main reasons. One, because we see that it's very powerful and very successful. So we also, for our weather forecast, are embracing more and more artificial intelligence, machine learning methodology. So we now also have an atmospheric machine learning model in operation at ECMWF, producing forecast on a daily basis. But for Destination Earth, we want to take it one step further. We also want to develop with partners machine learning variants of all the different Earth system components, but also for the impact sector applications. And for us, it's really important because it allows us to become much more interactive. You can imagine it running a model, climate scenario or an extreme weather simulation. At the moment, takes a lot of time, days, hours, days, sometimes even more. Which prevent us from being a very interactive tool, because you usually have to wait very long before you have your result. When you can switch to a machine learning application, of course, the training will still take very long, but it's an offline process. But the inference can be very quick, so that means that the interaction with the applications can be much more better. The experience for the end user can be much better. You can run many more scenarios than what you currently can do. So an example where we have this tight integration on the model level, so completely on the left-hand side, where we actually couple the models directly on physics layer, kind of, if you want to say, if you want to call it that, where we have a national regional initiative for a digital twin called Glory, which is an initiative from Germany and Switzerland, but also Italy is heavily involved. Here you see an example of the northern Italian region, where we take input from Destination Earth, use that to initialize a regional model over Italy, both an ocean model and an atmospheric model. These models are then also coupled, and we use also a coupler to then write the output of these coupled models into the Destination Earth data handling services. So a lot of coupling, a lot of interfaces. This is actually quite an interesting project for us to understand how this interfacing could work and interoperability could work on many different levels for a single project. If you look at some examples here, you can see this coupling is actually quite powerful. If you look at the bottom, you see the precipitation of a flooding event in the northern part of Italy. On the right-hand side, you see an uncoupled model where the prediction was not that great. In the middle, the red box, you see that if you have like coupled models where you also include the ocean, we can actually, using initial boundary conditions from Destination Earth, predict these extreme weather events pretty well. Another thing that, of course, is quite interesting as well for a lot of applications is the ability of Destination Earth to create so-called what we call storylines. So we take an extreme weather event and project that into past and future climate conditions to understand what would have happened in the past, what could happen in the future, to also develop more powerful mitigation strategies for these extreme events. So anything that is related to environmental stress scenarios, so in interTwin, there are already several cases where this is highly relevant. This could be a very interesting opportunity to link and interface with Destination Earth to tap into these climate extreme event scenarios for future climate states, basically, and tap and link it to your application to run scenarios. So here's my last slide. I wanted to basically also challenge a bit the audience to come up with new ideas to link with Destination Earth. So of course, as I mentioned before, we're really looking at like more tight coupling for digital twins with Destination Earth. We're looking at scenarios where digital twins can feed back into Earth system models potentially. Maybe we want to look also into accessing much higher resolution data from the model directly, right? So not after it has been being produced and written to disk, but directly tapping into the model outputs when they're being generated by the model themselves, and also integrating impact sector application more directly into DestinE. So we want to have many, many more arrows between interTwin and Destination Earth, or projects that use interTwin. And of course, we have been exploring some of these interfaces to understand how they could be implemented in practice. But we expect going forward that we will have many, many more of these exercises with different communities. And that was what I wanted to talk about. Thank you.
Thank you, Thomas. Question from the audience, also related to the last point. Okay, please. Again.
Hi, Thomas. I was curious at to which level can one validate these simulations looking into the past? Are there data for that?
Yeah. So we're doing different validations. I didn't present the slide on that one, but of course for past, our models should be able to reproduce past climate, right? So there we can run these comparisons. So typically a climate simulation you spin up like 20, 30 years ago, because also the ocean has to need enough time to move the heat it absorbs from the atmosphere all the way through the deep ocean and bring it back up. In other places where these ocean currents resurface to the resurface, so you need to start this climate simulation anyway, like 30 years in the past, right? And then you can validate if they predict the past climate correctly. That's one. Of course, then you have different ways of validating climate scenarios also for future scenarios, where you can link it to seasonal variability and so on to understand if your models are still reasonably close to what you expect from a physics perspective. So there's a lot of validation going on for these climate simulations.
Yeah, another question?
Thank you. Thank you, Thomas, for this very nice presentation. I represent here the coastal engineering community, and I was looking at different ways to couple, and we are developing digital twins for the coast. I was looking at the ways we can couple with Destination Earth. So my question is, I would say we'll be on the right-hand side for uncoupled applications. Are you planning to have regional downscaling from your global simulations, like, for instance, the Copernicus Marine Service does? So we could link to higher resolution predictions that handle, for instance, the localized phenomena that can, for instance, trigger flash floods.
Right. So one, we had actually a use case with Deltaris on coastal hazards in interTwin that we also had in Destination Earth. So that was for us a really nice example to explore how a digital twin that would run in the interTwin context would also run in the Destination Earth context, and how we could make that interoperable, but also transportable, right? So you can deploy it in these different environments, make it more portable. The other question about downscaling, so there's a couple of things there. So yes, in Destination Earth, we are developing these methods ourselves. Then there are solutions available, not developed strictly speaking by Destination Earth, but hosted by Destination Earth. So on the DESP, so on the central platform of Destination Earth, there's a lot of applications available. If you log into Destination Earth today, you will find that there's lots of applications, and some of them actually doing this kind of things. So I think there's also applications that, for instance, downsample Era 5 data as an example. So there are services there that can do these kind of things. And obviously, you're also free to develop these methodologies yourself and make them available to Destination Earth as a service. And then use it yourself or offer it to others, you use that as input for your digital twins or impact sector applications.
Okay, thank you. I think we can move to the next talk. Thanks a lot, Thomas. Okay, so Thomas, I mentioned quite a lot of interTwin, so now I'm going to introduce the project for those, of course, that don't know it. Waiting for the slides. One, four. Okay. So I'm now going to introduce the project and the main achievements, given that, of course, as I mentioned before, we are finishing the project at the end of August. So interTwin is developing a prototype of an interdisciplinary digital twin engine for science. We have piloted this developments together with the diverse use cases coming from the environmental and the physics sciences. And what is the digital twin engine that we have developed is a software infrastructure which is managing and supporting the design, this deployment, and the operation of digital twins. So, you know, among the functionalities that we are delivering is orchestrating the data flows, providing access to resources and infrastructure, enable services, simulation, and data fusion, machine learning, and other things. The project is started in September 2022, so we're finishing in August, as I mentioned before, and we have been like building the consortium, putting together different type of stakeholders. So, you know, from one side you have the providers of resources. We saw that, of course, in this particular type of domain, we need different type of resource provider because they have different needs. So from one side, you know, cloud, but also HTC and access to HPC resources. So to have like an hybrid layer of computing infrastructure. Then we have like technology providers for the which are delivering the components, of course, of the software infrastructures. And then we have like many representatives from the communities, the domains. We have 5 domains. So among the 2 micro domains of environment and physics, we have like also 5 subdomains, let's say, that are developing the use cases. They have developed the use cases and also contributing to thematic modules that I will show later. So we have like 2 different, as I mentioned, over the 2 different domains, and the use cases are the climate research and environmental monitoring use. We have like 6 different digital twins applications that we are finalizing now in the last 3 months of the project, going from the extreme events detection, impact modeling of also extreme events, and there are different institutions that are contributing, like CERFAX, CMCC, CNRS, EURAC Research, Deltares, the Technical University of Vienna, and University of Trento. And then we have the physics use cases that are contributing also, they have contributed to design, of course, the components. We have like different use cases going from radio astronomy, Virgo gravitational wave interferometer, lattice QCD, energy physics, with CERN, CSIC, the Max Planck Society, KNFN, and the ETZ as well. So we have, you will see, of course, in the next presentation more details, and in particular 2 of the digital twins that we have developed with more details. The architecture of the system, simply, you know, high level, is basically composed by, so it's mainly for the developers, so the expert users that are building the digital twins using what is being delivered by the digital twin engine. We have a layer of, on top of the physical resources, of course, which provide AI, orchestrating the resources, federated compute, and federated data management. Then we have a core components, which are like workflow, data fusion, real-time data acquisition, which, and then a set of thematic modules, which are tailored to the needs of the digital twins application. which are built and then made available to end users, let's say, that are accessing the final, let's say, result. The implementation is available, so basically we've completed the final release in this 3 months, the last 3 months. We have, of course, everything is open source. We have included in our GitHub community all the components that have been, let's say, developed from scratch. Of course, we have a lot of components that have been open source and reused or extended during the project. We're building also an open source community in order to continue the development and the support, of course, of those components. In particular, the one that I want to mention is the component that we're using for Computing Federation, which recently, in March, has been also, let's say, become a project into the Cloud Native Foundation, so the open source endeavors will continue also in this context. So we're a bit late. I'm not going to be like going details here, but I just wanted to mention that we have like components for the infrastructure, which will be detailed later by Isabel in the next presentation. Components for core, which also will be detailed later. And what is important also for the developers of the digital twins is that, of course, all these components are available in testbeds. So we developed the services and deployed in the different resource providers that we have. So they're accessible from a dashboard, so you can access the different services from there. And what is also important, I think one of the main outcomes of the project is that those testbeds allows, compute and data federation, which I will explain more in these slides a little bit more in details. So we have like a common, system that where all the services are accessible from the same AI system, which is the Charis Chatzikyriakou, which is coming from the EGI portfolio of services. These main services are deployed on clouds, so we have several clouds, that are participating in the project, apart from the EGI Federation and also externally, using like Tosca-based deployments. And then those services, which allows, interactive computing, serverless computing, access to Earth observation and data, they can offload part of their computation, which are like need either GPU's access or HPC to HPC providers transparently, which is a component which will then deployed later, detailed later. We have like 3 main HPCs that we have used during the project also for prototyping and for access: EuroHPC Vega, the Jülich Supercomputer Center, and PSNC. And then we have on the side of the data part, there are like a federation of storage system, which basically allows the transferring on data from data repositories directly into the HPC system and then accessible, for the application and for the computation directly there. So this is like the big picture of the Compute Federation that we have developed, and will also be detailed later in the next presentation. So going quick, okay, we have also more sites in the picture, so we have also integrated, for instance, KBFI and CESGA. So now we will go more in details on the outcomes, so the technical outcomes. Isabel Campos now will continue to show you this, and then we will have the certificate outcome from Charis on the EODC, and then finally the impact from Xavier Salazar. Thanks a lot, and I will take some questions now. Any question? Otherwise, we move to the next talk from Isabel. There is a question.
Thank you, Andrea. My question is about this distributed computer architecture. What justified the use of 3 sites, and how did you decide which model or which engine part runs where?
So basically, not all the, let's say, HPC are connected to anything. So basically, now if I go back, so now the big picture I wanted to show, the different connection, but there are, each HPCs is delivering and having different capabilities. So for instance, we know that in some HPCs we can run, for instance, Jupyter, because they allow, for instance, external connection connectivity, while, for instance, others, they cannot. So depending on the capabilities that are offered on HPC side, we are delivering different type of computing. So we know that interactive computing can be run in one side because they allow it. In others, they are more restrictive, they cannot, so we can do more batch. So it depends on the type of and the policies that they have at HPC side, that we decided to have different type of HPCs instead of like maybe have access to only one, which was kind of more restrictive, and we could not do the whole spectrum of computing access that we need. Okay, so if there are, I don't know if there are more questions, then we can move to the next. Isabel. You can use this.
These two passes. I prefer this than... No? Yeah. Okay. So, waiting for the slides. Yeah, you can put the work package, the technical. You have to change the slides, no? Yeah, the second tab. Or the fifth, yeah. No, not that one. It's open. Yeah, okay, thank you. That's the good one. So I will describe in this presentation what we call Work Package 6 and Work Package 5, dealing with, one is the development of the core functionalities to deploy the digital twin engine, and the other one is the connection with infrastructure. This is something particular, as we know, in this realm of projects related with EGI, etc., which we are not happy with developing only. We need to have a testbed, we need to have an infrastructure to deploy it, and this is the spirit a bit of this work. I recap here the slide of Andrea. This is the global architecture of the digital twin engine, and those are the two layers that I will describe now. Okay, we had we will have, I want to advertise it first. Okay, this is our plenary session on digital twins, but yesterday we had a number of presentations related to it that are described in this. And in the poster session, we have interTwin AI and the impact framework also displayed. So, core tools. So the middleware stack of the digital twin consists of the core tools plus the connectors to the infrastructure services. Yeah? The infrastructure exists, but as Enol points out very often, the compute continuum does not exist yet, and we need to make it happen. So there are a number of developments in the Work Package 5 to try to alleviate that. Yeah? So this is the graphic which Matteo, who cannot join us unfortunately, did. This is essentially the virtuous cycle of the digital twin engine development. No? So we want to interface with components and high-level services and provide the playground infrastructure that will support those execution, because we are at a relatively medium TRL level. Yeah? This is not a production thing yet. The core components that were existing before the project and that have supported the development are these ones. In this slide, we have the infrastructure manager, which is present in many projects, has been extensively presented. We have Oscar. Oscar is an open source platform to support event-driven serverless computing. We will come to that later. We have the SQS services that is about, let's say, software validation, service deployment validation, etc., that is being expanded to do as well the model validation. OpenEO as the API interface to connect to Earth science observations, the workflow manager of CMCC, Pyophidia, and iProf to support provenance and management within scientific workflows, which is one of the key aspects of a digital twin. You need to validate and you need to know from where things come. Yeah? So from these components that I said were pre-existing, a number of developments took place during these years. Those are in blue, the blue icons, let's say, are outcomes directly of interTwin. And then some are more, let's say, individual products, the ones inside the box, and then, let's say, more products that are composed of the previous one plus some other developments, which are DestinE and interTwin AI, which is a comprehensive machine learning environment, as we will describe. Okay, this is the first part of the core developments. Advanced workflow composition, real-time acquisition and processing. This is a key requirement for any digital twin, because we need to compare the simulated result with the evolution of the reality. Yeah? And this is the essence of a digital twin, which is not a simulation. Yeah? It's not just a simulation. We need to monitor, testing with real data, etc. And that is proving to be very challenging. We don't have so much middleware able to deal with real data and then send the simulation to an HPC or to the cloud or whatever. Yeah? So this has been a challenge in interTwin. So we have been integrating these workflow supporting tools for real-time data acquisition. They are connected now with infrastructure services and embedded with data processing capabilities directly accessible to the end users. This is Oscar, who has been our workhorse. Somehow it's an open source platform for event-driven data processing. So for those not familiar, event-driven processing consists in software that reacts upon events as they occur in real time. Yeah? And in interTwin, we focus on storage-related events. Yeah? Meaning that when the user or the sensor or whatever uploads data to some selected storage, for example, the cache, this example, no? An event is generated, and that generates a job, a computing job that is executed in a cluster that is instantiated by the Oscar service. Yeah, so you see more or less the workflow. OpenEO has been integrated with Oscar. This is one of the collaborative outcomes of the project. So now OpenEO can also, let's say, instantiate Oscar clusters and use it as processing backend, which get offloaded via interlink to HPC systems. Yeah? So the final product, let's say, interTwin branded, etc., is called DestinE. It's a data connector through Apache NiFi for Oscar. Yeah? This has been developed entirely within this project. NiFi is an Apache project, but it was initially developed by the true experts in real-time data movements, the NSA, yeah? That then they made it open source and gave it to the Apache Foundation. So NiFi automates and manages the flow of data between many, in principle, disconnected systems. And it helps to transform data and route them to the proper place. Yeah? This is the architecture. So the way it works is the user creates an Oscar service, also defines how the data flow has to happen through the DestinE interface. That at that point starts monitoring the cache, for example, if this is the storage that we are using. It captures the events, Oscar runs the job, and uploads the output of the job to the cache also, or to wherever we want to upload it. Yeah? And then you can download the output. Yeah? This is more or less the user flow intervention. Yeah? Another major component is the AI workflow and method lifecycle, so the support for machine learning. Yeah? This is a highly demanded feature for digital twins. So comparing the simulation, okay, we live days in which any new experiment, etc., has to deal with a very large amount of data, and everyone is in the hope that machine learning or artificial intelligence, etc., will help us to deal with those data by applying machine learning technique, neural networks, however you want to call it. So this has been also a challenge. So it requires an interplay among many components, analysis of large quantities of data, integrated with a workflow which is able to interact as well with DestinEos, embedded with data processing capabilities, connecting with infrastructure, is a true challenge. As we know, industry drives machine learning, but science in general requires dedicated solutions. It's not anything new, at least, for example, in the area of high energy physics for HEP data analysis. We had this TNVA software package since the 90s, and this has been a commonplace, no? Now there is a much more diverse ecosystem that relies on industry standards, such as SciP, TensorFlow, PyTorch, and all this, no? But our feeling is that the level of precision that is required for data simulation hybrid methods requires a much more specific research on uncertainty quantification and validation in this. So we need model-aware machine learning with custom architectures. So you need to teach physics to the machine learning algorithm. So that what comes out makes a bit of sense. And then there is also the generative models that can be used under some circumstances. You know, that is also not the panacea. Actually, what we are observing is that they can be used to help, let's say, classic machine learning when you don't have enough data, etc. But this is a subject for the future. Yeah? I put there the graphic of Virgo, which is one of our use cases that Charis will describe later. See that what we wanted to do is offloading from the user, which are those blue components in the middle. This is for the user or developer of the Virgo community to do. And the rest, what is really generic tools or the infrastructure side, is taken care of by the components of interTwin. Yeah. So we leave, let's say, the physics part on the physicist and what is more generic on the core components. And so was born EGI2025, which has been developed in the project by our colleagues at CERN and in Jülich, which is an open source toolkit designed to accelerate machine learning. It is scalable, it is able to interact with HPC resources, there's ones in Vega that we described. And as I said, it focuses on reducing the burden on researchers. Yeah? They don't have to deal directly with the AI or machine learning tools. Yeah? It is connected to MLflow. It can generate its own model database. So it's really a project is under development that will, I think, will gain some traction in the next years. This is EGI2025, in a very schematic way. So it's connected to all the other core services that have been developed. And this is how it looks inside. So these are the capabilities. Distributed machine learning, connection to PyTorch and TensorFlow, hyperparameter optimization, provenance, quality assessment, and the connection with the infrastructure of interlink. Yeah? And as I said, they create this machine learning models registry that can be created. Yeah? The model validation and uncertainty tracing, that has been the task of several of us, has consisted in the development of a customizable software toolset to enhance the digital twins with the capability to implement best practices in quality measures. So a simulation, as pointed out before, is not a digital twin. You have to prove it, no? And to prove it, you need to show that it corresponds with the evolution of reality. And this is validation, yeah? It is the action of, according to Wikipedia, the action of checking or proving the validity and accuracy of something. So this is validation. And the comparison and feeding with the input real data is key here, obviously. The automation of the validation process is needed, especially when the data amounts are prohibitive for individual validation. Yeah. What is the strategy? As we can all guess, validation is highly model dependent. Yeah? So we have designed a use case scenario which is generic enough, perhaps to accommodate the most generic cases. We have enabled the SQS platform to be embedded in the steps of a validation workflow via a command line interface. We integrated very useful capabilities related to data provenance via iProf, which is now talking to the SQS system. And then, yeah, with this strategy, it is up to the developer to pick the tests that need to be done along the workflow to validate with real data what the digital twin is simulating. Yeah? Okay, this is a bit more complex for the slide, but there it has we have, it's a bit the project status, yeah? It's the validation of the PyOphidia workflow description is there. We have a data quality model connection with iTwin AI. That is really very early in project time, was already done. And the integration with provenance tools, where we created iProf for SQA, which is a provenance library to track the software quality assurance processes. And here, Sandro, they are even writing a publication about it, and to the middleware 2025 conference, which is under submission. So this is, yeah, has been an interaction born from the project. Yeah, and now I will go to the connectors with the infrastructure. Do you have any question about the core components? Or before I move, Anabela.
Well, you gave me a lot of things to, to analyze. I have a provocative question. I need to build a digital twin for cultural heritage. How do I start using your interTwin's components?
For cultural heritage, what is the real system?
Well, the real system are monuments, and we have a lot of data sources like laser technology to monitor in continuous way the monument. We have image evolution for degradation. So the concept here is making monuments available to the public and at the same time monitoring their evolution to schedule interventions of rehabilitation.
So you need to, first thing you need is DestinE, which is the real-time agent able to gather this data that I suppose you have drones, for example.
For instance, yes.
The images,
yes.
So this needs to move to some storage, no? Which is at your center or wherever. And there you can install some real-time or event-driven application through DestinE, which will be able to deploy an OSCAR cluster, and there analyze what is the status according to the parameters you want to put. No? I guess that depends on what do you call degradation, no? So this is something that's interesting. So you need to define a workflow, so to say, using DestinE that processes those images and gives you the levels of that you are interested in, yeah? Where intervention is needed or not. But I would say you can do it with, if you use machine learning for that, then you can include interTwin AI to do the data analysis, the image analysis, possibly, no? And yeah, maybe we can think about it. That sounds like a nice case, no? But I think the components are there. from the
Okay.
core point of view. Yeah.
Okay, thank you.
Yeah. Okay, so
Okay, we can continue.
Yep.
Yeah, we're a little bit late, so we have to.
We continue, yeah. So the connection with infrastructure is handled by the Work Package 5, which is coordinated by Daniele. These are the main components to deploy the infrastructure. Interlink, that has been developed in the project itself, and Teapot as well. And then Alice is an open source for linking accounts on HPC system, also recently developed. Yeah. The rest of components we know for some time. It's Ruthio, the FTS, the Apple accounting, the AI-based orchestrator has also been, let's say, further developed in this project. This is how things are made. You have a middleware toolkit to connect to the infrastructure. This is the interlink, the storage tools, Teapot, Ruthio, FTS to move data, and Alice to authenticate, the Indigo Pass Orchestrator and Apple for accounting. And we managed to make display with computing and storage capacity, which is something we do really in many projects in a standard way. What are the differences? So we have a federated computed infrastructure, and this time we extended container orchestration via Kubernetes to support the execution of a physical node of clusters. So it is able to execute on HCC, on HPC, on the cloud, etc. So we are trying, as you see, to approach the compute continuum with this strategy. This is just an image of the integrated topology that we have with the centers described before, Vega, Jülich, and PSNC for HPC. And then we have cloud resources as GRNet, EODC, and UCRI. And we will also have integration with a quantum system at CESGA as last item of this task. So we'll integrate quantum computing in here. This is just the map of the federated infrastructure for the data lake. Yeah? So we have many people contributing to the data lake. Vega in EuroHPC, because they are more open to these solutions that other centers. So it's working rather well. And we developed, as I said, Teapot, which is ready to be used to support integration with the data lake. Paul is here, can answer you about Teapot. Yeah, and Diana. These are the numbers of Vega is a large machine in the pre-exascale list of EuroHPC. Poznan, PSNC has really many resources, and I think we could test things on HPCs very easily. We had less access to GPUs. That is true, so this is coming up only now. They are scarce resource, GPUs. We have 11 storage providers across Europe, which are described in this map. The data sets, a bit more than 130 are there already with all sorts of types, data types, NetCDF, TensorFlow records, etc. So this is being handled in collaboration with Destination Earth to make sure that things will be supported for the data types that are more common. This I will probably slide. The cloud HPC integration via interlink, also embedding interTwin AI for the workflows. And I finalize with the conclusions. This is a challenging project. We have computing challenges. Yeah, it's much to develop and integrate it, and still needed to bring it to a higher TRL, near real-time data processing. We had to identify a model validation framework, develop the tools to enable the compute continuum. And the data challenges are also massive. We really need to work on reproducibility, not only from the data and results point of view, but also from the software tools, etc. This is what I label as 360-degree reproducibility. That is. Will machine learning eventually help? Maybe, but currently fast machine learning simulation techniques, for example, for HEP detectors, require thousands of models. We have, in one of the use cases, deal with just one model and one type of material, etc. The digital twin of a detector of HEP is a massive undertaking. That is a true challenge. Yeah. But we put the first brick on that wall, I think. And I leave you there some old minutes from a meeting at NASA on the 1970s, describing the challenges of digital twins. And yeah, we are asking ourselves very similar questions, no? So we are trying to identify how to do this co-evolution of the digital artifact, how to validate that, which validation criteria we have. But I find it curious that we are still on this discussion, no? After so many years. But, I think it puts this in perspective. Yeah. Okay, that's all.
Thanks a lot, Isabel. So we have time for a quick question. Any? Yep.
Thank you very much. I have a question regarding generative AI and machine learning AI. Because, well, in some cases, for example, we have videos that are produced to monitoring, and sometimes, for example, generative AI is using to, when we have some problems with image and stuff as that, use it to generate, to complement. Do you think this kind of complement could be added in your system, or how could be possible?
I would say if you have the software ready to do that, we are technology agnostic. You can embed any piece of software that can fit in a workflow. Yeah. Whether it is a neural network or is an additional process to generate more images. In that sense, the architecture is completely agnostic. There is no limitation. The applications that you plug in, for example, we have generative, these GAN adversarial networks, no? This is generative somehow. We also have generative applications in the lattice QCD simulation. So, but this is completely agnostic from the core. So it's just whatever the user wants to do.
Okay, thanks again. So thanks, Isabel. And we can now move to Charis for the outcomes.
Good morning, everyone. Do you hear me properly? Yeah? I guess so. So good morning. I am Charis Chatzikyriakou from EODC, the Earth Observation Data Center in Vienna. And we have been leading, somehow I'm in the mode of closing the project, so I might be using past tense. As Andrea mentioned, the project still has 2 months, but I'm somehow in the past tense. We have been leading work package 7, which has been focusing on the development of thematic modules. And today I would like to give you an overview of the scientific outcomes of the project. So, excuse me, the thematic modules and the use cases that Andrea already mentioned. Briefly, I will give you some more details. Quickly, the outline, introduction, how the DT applications and the thematic modules fit in the DT architecture, then an overview of all the DT applications that we had in interTwin and the developed thematic modules. Then we will have a closer look into 2 of them, one from the physics and one from the environment domain, and then we will close with some conclusions. So in the introduction, what was the approach that we followed in interTwin? Why did we have use cases and DT applications? Basically, what we wanted to do is to co-design the digital twin engine with different scientific communities from different domains. So basically, we want to understand in depth their functional and non-functional requirements. And as you can see, and as you already heard, we focused on two main domains, physics and environment, because of the different challenges that they would create, right? So on the physics side, we have the data-intensive and compute-intensive requirements, and we had more specifically high-energy physics, radio astronomy, gravitational wave astrophysics. And on the environment side, usually we have challenges related to data fusion and accuracy, and there we focused on climate research and environmental monitoring. The assumption was that although the use cases come from different domains, they will share, or anyway, it would be nice if they could share a common set of functional components, and based on this, we thought that the developers could benefit from common software products. Therefore, they participated in the whole cycle of the development, as you can see in this graph. So the design and evolution, the integration and the validation, and of course, they participated in the development of the thematic modules, in the thematic components or modules, it's the same for now, which are specialized to their community. I think this we saw already, so just to briefly say that we are focusing on the top part, the thematic modules that are still part of the engine, of the DTE, and the DTE applications that are implemented, that are enabled by the DTE. And now starting with the applications, with the DTE applications, on the physics domain we had 4 of them, starting with QCD, a digital twin for QCD simulation. You see me, I'm going to be consulting my notes because it's a lot of information and I cannot remember it by heart. By CSIC, here from Santander. The second one is from MPG, the digital twin to simulate noise in radio astronomy. Then we go to Virgo, already mentioned from INFN, a digital twin to simulate noise in the Virgo gravitational wave interferometer. And finally, the use case of CERN, which built a particle detector data-driven digital twin for high-energy physics. On the environment, we had, oh, sorry, what happened? No, sorry. I wanted to say that for all these, for the 4 physics use cases, these must be 10 thematic modules were developed. I cannot go into detail now because of time, but I have put the link to the website where you can go and look at them into detail. They have been developed, as I mentioned, by the different scientific communities, and they focus on specific needs of the DT. On the environment side, we have 6 use cases, and starting with the use case from Deltares, deploying FloodAdapt, which is a digital twin for flood impact modeling anywhere on Earth. Also another use case from Deltares, a digital twin for flood early warning in coastal and inland regions. The 2 use cases from CMCC with collaborators, a digital twin on projecting the occurrence of tropical cyclones due to climate change, but also wildfires. You see at the bottom, a digital twin for drought early warning in the Alps by UREC and collaborators, and finally the extreme rainfall, temperature, and wind as a result of climate change. I'm sorry, I really need to cough. Okay. Again, a number of thematic modules were developed here. As you can see, they serve different purposes. For example, processing and analysis of data for the different use cases for cyclones, for wildfires, for eddies, downscaling data, some specific ones for using OpenEO, like running OpenEO graphs or storing stack metadata, and so on. Then more on the flood side, there are a number of modules developed by Deltares and collaborators for assessing the floods, the flood impact, or economic impacts, and so on. Please go to the website to check them out. Now I don't have time to go through them, but there is very nice documentation about them on the website. There has been work put into this, so it must as well be appreciated. And now I can move on to the two use cases that I will tell you some more things about, and starting with the physics domain, the digital twin, to simulate noise in the Virgo gravitational wave interferometer. What was the challenge that this use case wanted to address? So the gravitational waves are ripples in space-time caused by the acceleration of big objects like black holes, as you can see in this image. And we want to investigate them as they provide a lot of insights when it comes to cosmology, early universe, fundamental physics, and so on. The problem is, though, that the data that come from the interferometers contain a lot of noise, as you can see in this on the left side. And more specifically, the transient noise, or glitches, as I'm going to call it from now on, poses the biggest challenges because they has as a result that they can hide basically the gravitational wave signals. We can miss them because they mimic them a lot. I'm not a physicist, but I'm telling you what I learned in the project, right? Maybe not everything is extremely accurate. What we wanted to do here, how we wanted to address this challenge, is to develop a DT of the interferometer that exploits generative models to simulate this kind of noise, these glitches, from control channel data, and perform denoising and vetoing on the data. Vetoing is when the excess energy seen in the data is completely accounted for by the generated data, and the data then is not flagged as interesting, and then we save resources by not having to study them anymore. And the denoising is when the generated data is subtracted by the actual data, and the outcome is used for further analysis, so to improve the data quality. When it comes to the structure of the use case and the use case component, here you see in orange the infrastructure modules that Isabel already introduced. You see in gray the core modules, also introduced by Isabel, and in black, or what that is, the thematic modules. Staying in sort of in high level, the use case was, the DT application was structured in 3 main phases: the training, the data management, and the inference. When it comes to the training, you see Analisa, the Analisa component, which is the channel selection algorithm. You see the pre-processing API, which was responsible for resampling, frequency bypass, filtering, whitening, and spectrogram generation. Then we go to the glitch flow, which was one of the thematic modules developed for this DTE. It was also in the previous slide, which maps the control channels that are interesting to us. Basically, we want channels that are sensitive to glitches, but are not sensitive to gravitational wave signals. And then we have, okay, there are more components, I cannot go through all of them, but then we have the inference, where the pre-processing API takes place. Again, the generative API loads the model from the model registry and feeds new data into the glitch flow to make the inference. And finally, the vetoing and denoising module, which basically performs the vetoing and the denoising. And it saves the metadata at the end. On the data management side, 2 Rusio storage elements were created, one on the interTwin data lake and one on the INFN computing center. The files were transferred via file transfer system mediated by Rusio, and the interTwin data lake was storing unstructured data plus the necessary metadata for the machine learning applications. When it comes to the integration with iTwin AI, the thematic module pipeline was implemented as a plugin, as an iTwin AI plugin, and it has integrated the logging in the model catalog for distributed training. Closing for this use case on the scientific outcome and outlook, or the scientific, let's say, impact, the model is able to correctly generate a glitch above the threshold signal-to-noise ratio, and they are generated with the right time and frequency, and with an accuracy of 97%. When it comes to the impact, the Virgo interferometer is willing to discuss integration of this digital twin into the official pipeline, which is really nice. And complementary tools developed for data pre-processing of the DTE are being used within the LIGO Virgo CAGRA collaboration. Moving on to the drought use case, and I think I have to speed up. Here the challenge is basically what the name of the use case explains: increased pressure on alpine water resources due to climate change, require advanced or more advanced than currently early warning systems to improve preparedness and drought risk analysis. The aim of this use case was to develop a high-resolution hydrological seasonal forecast system that integrates different kinds of data sources, heterogeneous data sources, in a complex and transparent modeling workflow. The structure of the use case is what you see here, basically three phases, again, 3 parts. On the pre-training, the surrogate model, I wanted to mention before that the modeling approach is basically that we calibrate the WFlow SBM hydrological model using a surrogate model and satellite soil moisture estimates. There are 3 phases. On the first phase, in the pre-training, there is the surrogate model, which is being pre-trained with deep learning methods, and the WFlow SB model is being emulated. In the second one, in the parameter learning, the surrogate model is being calibrated with satellite data, soil moisture satellite data, but also other catchment statistics. And in the final part, in the inference part, the hydrological seasonal forecast is being run by the calibrated model, using actually CSIC climate forecast. On the integration part with the other components, the legend is the same when it comes to the colors. So you see the DT developer and you see the DT user. You see the OpenEO boxes, which are the workflows, basically, and in the middle, again, you see the data management part. The DT developer can use and customize the HydroMD and WFlow thematic modules to set up the WFlow SBM hydrological model. The inputs and outputs are stored in stack catalog and accessed also through the interTwin data lake. And then the DT user can run the downscale ML to downscale climate seasonal forecasts. On the integration part, I'm finishing, Andrea, promising. On the integration part, these are the integration with the core and the infrastructure components. Basically, Hython iTwin AI plugin supports the training and calibration of the surrogate model on HPC. Stack is used for publishing output and intermediate data sets. Oscar to run the use case containerized components in cloud environment. And finally, OpenEO is used to manage and execute the overall use case workflow. On the scientific outcome, what you see here is a result on trying to predict, basically trying to see if we can predict the drought of 2022. You see 3 different seasonal forecast initiations, February, April, and June. In blue, you see the soil moisture data. I don't know if you can see the difference. Yeah, in blue dots, you can see the soil moisture data. In this gray continuous line, you can see the soil moisture climatology from 2000 to 2020. And then these box plots represents the uncertainty of the forecast. As you can see, for now, it has not been able to forecast it, which is under investigation, because the box plots, the uncertainty represented by the box plots are larger, are higher than the actual soil moisture. So this is for next steps. I feel the pressure, so I will not talk about the outlook of this use case, but quickly to say that we successfully prototyped scientific digital twins in interTwin, 10 DT applications, 26 thematic modules, a plethora of cross-domain integrations with infrastructure and core components that you got an idea, but there's going to be also plenty of deliverables around if you are ready to read about them, and tangible improvement on model accuracy, uncertainty quantification, and real-time responsiveness. We still have 2 months. Some developers are going to continue and be finalized, but these are some stuff that I could talk about for now. Thank you.
Thank you, Charis. Quick question? The audience? Okay. Thanks again. We need to finalize with the last talk. Sorry, it was we speed up a little bit. So we have Javier now with the impact of the part.
Okay, so yeah. So let me see if it works. Okay. So I will also try to speed up because of better now. Okay. We'll also try to speed up because yeah, time is running very fast and I'm always putting the last part. So this is we have heard at this point. Yeah. Everything that we have been creating, like on the technical and the scientific side. And as we are coming to the end, it's also time to start speaking about what is the legacy and how can we follow up and what can you do as well to help this to happen. Okay, so yeah, to start with, I wanted to give a small vision on how the interest and the importance over the year has been growing. Yeah, so in EGI conferences, I recapped like the different sessions that we had related to interTwin, and in EGI2023 we had a small presentation, like, okay, so we want to do this, which, yeah, it further developed at EGI2024, so we got like a full session, like plenty presentations, part of the parallel program that we had for the conference. So we had a lot of developments done that could be presented and shared with the community. Yeah, and now we are here and we are in the plenary session. So yeah, you might think, okay, so that's a natural process of every project, but as well, sharing one personal experience. So 3 years ago, I was invited to present it into the EOSC community, into the EOSC symposium. It was also the day after the social event. It was the early session, and there were like 10, 11 people in the room, and that they didn't even know what a digital twin was. So over the years, so we managed to get a full session as well, organized, compiling all the different digital twin initiatives. And yeah, now we are again the first session after the social event, and yeah, we have a quite full panel. So yeah, we see that. So we have seen already like all these results, and we have seen already all the works that have been developed. So we wanted to highlight, we always need to highlight like what are the most important results that we consider that they will have a follow-up. And again, recapping the high-level vision of Andrea Manzi. So we can define that we have this whole interdisciplinary digital twin engine that it's compiling all the set of components. And we want to highlight some of them, like such as the AI framework that has a high potential for being adopted and is already being adopted. We also want to highlight the quality framework that it's also operational and it's being used widely across the scientific community. And as well, all the different tools that have been used for running the digital twins under the federated infrastructure. And as well, yeah, the digital twin use cases themselves, they are not part of our main results, but they have been the ones that have been proving and validating like the whole operations and the fact that they work well. Okay, and in order to do this, we had also to develop an interoperability framework to understand like what is the alignment needed between all the different standards across the different communities. So it was also a very important work that can be also reused. So all those results are available and will be kept being available and accessible. Most of them said before, so we are using open source licenses, and we are like every owner of every component, so has provides their own access and support mechanisms for each of those. And yeah, for each of the key exploitable results, we already have like some key exploitation, which means like for the interdisciplinary digital twin engine, so it has become part of the key strategies for EGI. So we will keep on working and developing like business out of the digital twin engine and the different components. It has become part of an operational service for the quality framework. The interoperability framework, it has contributed to improving standards. The federated infrastructure and the toolkit, so some key components are being further reused and further developed, and all this so is also supported under the open source community that we have created. Okay, so getting a bit more into depth into this, how we are reusing all these project results. So noteworthy to mention, so yeah, interTwin itself, it has been as well the driver of reusing and yeah, advancing on previous results, from previous projects. During the project, we have been collaborating with a number of projects, as Andrea Manzi said, like mainly in the digital twin domain, but not only, as well linked to the core components and the infrastructure components. Like we also got like some interest from projects developing infrastructure or trying to improve like the usage of infrastructure, especially HPC or AI. And we also had like some collaborations on the public authorities and on the end user domains. Okay, on the AppTech side, so some of those projects have been actually uptaken and have adopted like some of the components. And yeah, the major two flagship initiatives like EOS and Destination Earth. So they are not only using and reusing like the know-how, so they have also incorporated like some of the elements that are like on the operational level. And yeah, most important as well, many of the components are already following up under like projects that have been presented here. And yeah, obviously, any new project opportunities, we are always happy to listen. And so, translating this into business or outcomes, so we have been presented many software components and many elements. So, yeah, we had like 43 components that I think in these 2 months that are missing will be even increased. And as we were saying, like many of those are new developments, others are extensions over like already existing software supported by big communities. And what does it mean to create a product? So it means that we need to create like an entry point. We need to have like some support, to have like some specific websites for sharing and having all the documentation and different training material that has also been created during the project, and is available for you, for anyone that wants to use them. And here, yeah, I'm putting as example like interLINC and IT-WinA as it's some of the highlights that we have in the project. But yeah, we have for, I would say, almost all the higher maturity level software components. We have also improved services. And that's very important as well, because having a fully operational service is not easy. You need to define the whole process and how to make it work. So we have all this quality framework that is having quite a lot of usage. Also the infrastructure manager that it's being used, so it has developed all the capabilities for managing digital twins. And as well within EGI, we are developing, or we have been developing all this EGI HPC, or expanding our capabilities under HPC to the HPC domain. And yeah, the interTwin project has been instrumental as well for defining and for understanding what are the needs, and to incorporate some of the tools as well. So there has been a lot of work, but not only. So sometimes neglected in European projects are the standardization activities, and as I was highlighting, so all the interoperability framework, like having together, bringing together so many different scientific domains and communities, it's very challenging because everyone speaks their own languages, has their own standards, and being able to have compiled like a whole interoperability framework that helps like the different communities to actually use and access effectively like all the different tools, it's very important. And not only this, but some of the activities also led like to the actual development or contribution to already existing standards like the OGC that incorporated the OpenEO paradigms as part of the standard. And as well, we also collaborated with the, yep, oh, 1 minute, so I need to rush a lot. Okay, sorry. So we have been also contributing to policy making. So not only developing or collaborating with public authorities in some projects, or like developing like use cases that can be adopted by policymakers. We are like next month like having a set of discovery labs that where the interTwin or some interTwin use cases will be presented to policymakers, and we are also contributing to the Spectrum project that all this will be driven and is available under the open source community, so all the components can be discussed, can be used, adopted, and are supported by the community. And yeah, you can access the interTwin website is the main entry point, but as well as we were saying, we have the GitHub, and we have also the testbed that it's able to have, it has like some of the services or the different services deployed into the infrastructure, so you can also go and test and play with it. And yes, I think I will be on time. So as we were saying, 2 months before finishing, so there's still like a lot of work to understand like what has been the impact and what is the legacy. As in general for you, like any project ideas, if you would like to test or try out use cases, if you have like potential digital twin applications, we are happy to listen to you. And yeah, we are happy to engage in follow-up projects and follow-up initiatives. So if you have already a project that would need like some capability, we are happy to listen to you. So any questions?
Thanks a lot, Xavier. Any question from the audience or comments? Okay, so we will be here also today, so we can speak later also if you want to reach and discuss. Now I'll give the floor to Gwen. Gergi, sorry.
Thank you. So let me be really fast. We take the next few minutes as an opportunity to thank all the people who made this event a success, and to thank and congratulate to those who deserve the prize for the best poster. So if I can have the first slide set for that, that helped me remind with the names. No more interTwin. Prizes, thank you. We can hear about the digital twins in one of the parallel sessions after the coffee break. So we don't let you go without further digital twins. So first of all, I would like to thank you for the members of the program committee. I chaired the program committee, and it was quite a challenge to review. I don't remember, Gwen has the statistics on the number of applications we received across the different talks, posters, demos. It was a challenge to choose those that could fit into the program. Also keeping in mind one of the recurring feedback of not to have too many parallel sessions, because then people miss out those sessions that they cannot attend at the same time. We don't have digital twins for ourselves yet. We have the names hopefully soon, so just to give them visibility. Not all of the PC members could attend the conference, which was a pity, but understandable, it's a busy month. So I would like to thank again those who physically attend and those who couldn't be with us today. The next slide, if I can just quickly, it's coming, okay. So just to say a few more words about the PC. It was assembled based on considering different expertise that is matching the topics of the call that we had across the different domains, and also diversifying between infrastructure provisioning, platform expertise, and scientific community expertise. And if I get the next slide really now, because I don't want to keep you away from the coffee break, and I want to jump to the poster announcement, which is okay, we have a nice picture of ourselves from yesterday. And that was the list of the PC members, so thank you again for them. And then please go to the reveal of the best poster winners. In where I can click it, I should click it, okay. Yeah. No, I shouldn't. Okay, so congratulate to the 2 winners, because they received the exact same number of votes. So first, Anka Hianola, who has a poster on OS Trails. You can stay here until we get the gifts. My daughter's favorite, so they are really Thank you. Thank you. And just stay here for a second. And Zdenek, who informed us about the recent new features of the EGI notebooks. Congratulations. Thank you. Thank you. Thank you. Continue with that. Thank you. Thanks a lot. So then let's move on to thanking, first of all, our local host, George and Isabel, again, for hosting the event and making it a success in this beautiful venue and with gradually increasing good weather. After that, thank you for Marie-Louise and Beryl, who helped us with the registrations. So they are in the middle. And taking care of the shipment of all the stuff that we received, including the banners and including lots of posters and stuff. Thank you. Thank you. And then next one is Marcos. So come on, DJ Marcos, the man of the night, and the wizard for the audio connections and the Zoom and everything. Last but not least, to the local organizers who work on the logistics, including the catering, I think, and many others. Sorry? They are in the other place, brewing the coffee for us, so let's be quick. And then just a few reminders of how you can further engage through the VUVA with us. There is a new survey about Cloud Federation priorities where you can raise your suggestions on how we could improve, should improve the Cloud Federation activities. And by the way, there is also an EGI Federated Cloud meeting, I think, one of the last sessions today. So you can also join that and engage directly with those who run this. There is still one more question to fill as input for the new EGI strategy. And if you fill all the three questions, so there was one the day before yesterday, one yesterday, and there is one new today, then please go and collect your extra gift from the EGI booth at the entrance or registration desk upstairs. And there is still a photo contest open until 5 o'clock today. So post your best photo on VUVA, get likes, and if you are the one with the most likes, then you get an extra gift. And I think the last one is about the leaderboard. So it measures basically in VUVA how you engage, how you post, how you interact, how you message, how you do this and that in the platform. It gives you credits, and those who will win the largest number of credits by 5 o'clock today will get another extra prize. So I encourage you to use the platform even further. So I think that was the last slide, and I let you enjoy the coffee break. Thank you very much.
exemplified here.